Hi everybody, welcome back to the channel. This is the fourth installment of the Precast Concrete Lifting course delivered by our Technical Director Matt Collins. In this video you'll see some wall panels coming off a truck and being tilted. So they're lifted off the truck and they're tilted in the air. The side lifters are used to rotate the panel and then the top lifters are used to take the vertical load when it's been put into position, just like you'll see here. So the guys have it all unhooked. It's now vertically, it's going to be lifted into position. These will be very tall, slender panels. We would do this on stadium jobs where we would have kind of vomitory walls. We did it on the Everton project, but unfortunately we can't just show photos or videos of that at this stage, hopefully in the future. So I kind of trawled YouTube myself to find some Creative Commons videos that we could share, and these are some guys over in America doing the exact same thing. So you'll see here a better view of it, where it's just been taken off the truck. The lads are under mute now, they're taking off the lifters here, and then you'll see it just lifted vertically with the top lifters. So these are very tall panels, very slender panels, and they're handled very well. Again, another advantage with this is that you'll see here the guys are able to, well, they're putting in their clutches first and foremost, but they're able to put their props on the walls. So props are fairly heavy, especially for tall walls like this. So it's good that they can put them in on the ground, they can bolt them onto the wall. The wall can be tilted up in a nice controlled manner with the props on, and you'll see when the wall goes into place, it's very easy then for the guys to lengthen out the props and prop it back down to the slab. Okay, so we'll give you over to Matt now for the fourth installment. Thanks again for watching, guys.
This installment is, I suppose, different from the previous ones in that we're speaking about bespoke lifting in terms of rebar and strand. So the calculation of the demands remains the same way back in the first lecture, and in the previous two lectures was all about lifting using castings such as spherical heads or wavy tail sockets, and they had specific sets of failure modes. So with rebar and strand, it's a little bit different, and we'll talk about that over the course of the next 50 minutes or so. So suppose these intro slides can nearly be done away with at this stage, but the usual, we'll have time for a Q&A at the end. Leave your microphones off until the end, just so not to cause any interference. Course will be recorded. The handouts will be released at the end, along with the lecture slides. And if you have any technical questions, my email is there. We're over the halfway point in the course, and we're on lecture 4 now, rebar and strand. And then this is kind of the last technical lecture. Looking at the remaining lectures, all next week, we're just going to focus on what we've covered already, but in the form of worked examples. So putting it to practice what has been on the previous sets of slides, and then with I suppose the quantity of formulas etc. that are required, particularly for spherical heads etc. and the failure modes, the best way to approach the design is through a spreadsheet. So we'll give some kind of pointers on what a spreadsheet looks like and some hints and tips on how to create your own spreadsheet, so you don't have to write out the formulas every single time. So back to today, module 4 moves on from the typical lifting approaches to more bespoke lifting solutions using rebar and strands. I've listed the items here that we're going to cover today, and we'll begin with a quick recap of last week. But today we're going to look at lifting using rebar, lifting using pre-stressing strand, or lifting, and I suppose what's not on here as well, but also included, is lifting using wire rope. So there's 3 different kind of components, rebar, strand, and wire rope, that can be used for lifting purposes. At the end, have some calculations and work examples, and then we'll leave time for questions. Okay. Last week, quick recap. We focused on the shear. We focused on the shear failure modes. We took the general capacity formula here at the top and broke it down into its individual components for each failure mode. For steel failures, we showed that the rated capacity of the lifter is acceptable and complies with the approach taken using the explicit formulas. And that basically allowed us to show that it aligned with previous methods or the global factor safety methods, or when you're doing with tilting calculations, often the way to go was to just have the capacity. There are 3 concrete failure modes when we looked at shear. We had concrete edge failure, local concrete crushing, and concrete pry-out. And depending on the scenario that you have, either one will govern. We gave a description on how to reinforce against tension and shear failure modes using supplementary rebar. So we looked at concrete cone and we looked at concrete edge, basically a tension failure mode and a shear failure mode, and how to reinforce against them if, when you calculate the concrete failure mode, that your check does not pass. You have, I suppose, available to you to add in supplementary rebar, generally in the form of U-bars surrounding the anchor, hard against it, or in kind of a in the vicinity, and use kind of a strut and tie approach to prove that it's sufficient. And more often than not, the existing rebar is sufficient, so you can utilize the existing rebar in the unit for the supplementary checks, and you may need to just tighten up the spacing a small bit just to get them closer to the rebar. Following on from this, we discussed how to deal with tension and shear interaction. So because the forces applied to the unit through the lifter, the tension force and the shear forces, they're both being resisted by the same portion of concrete, and therefore they can't reach their full tension or full shear capacity at the same time. So there were some formulas that we presented towards the end that address those in terms of the shear and concrete failure modes. And then we finished off with a worked example of a typical case, basically right through to the end, and just generate a summary table so you can see on one page what results are for all your failure modes, what areas working the hardest, and you know what's the best way to adjust your design in order to get it to work. So that was last week. So this week we're talking about lifters using rebar and strands and wire ropes. So on the unlike the previous lifting solutions, lifting using rebar and strand, it requires part of the lifting component to be above the surface of the unit. This means that the lifting component may not be cut off after installation and potentially visible in the finished product. Thus, their application may only be suited to specific cases. I suppose any car park structure, bridge, anything where you have kind of an in situ screed that's going to basically encapsulate these lifting loops at the finished products. They can be used in. You can still cut them off, but obviously if you cut them off, the end is still going to be exposed. So if you had an exposed column, for example, that you're using lifting loops in that doesn't get patched up afterwards, you might end up having staining, etc. So just be mindful of the application that you're using it for. But in the likes of bridges and spine beams for car parks, etc., they're kind of valuable enough. So lifting, so we're going to split it out. So we're going to talk about rebar first. A lot of the, I suppose, parameters that need to be considered are to apply to both rebar and strand, but there are some subtleties. So I'm going to speak about lifting loops using rebar first. Any of these components are generally only suited to tension lifts only. So where you don't have any significant shear. There is some allowance in the code for the chain angle, and I have that on the next couple of slides. But the likes of tilting operations, you shouldn't carry out tilting operations using rope and strand. you'll bend the bar too much and cause fracture, or you'll kind of create a pinch point and cause damage to the precast. So this extract from the code here kind of states the requirements for the rebar material, and generally B500 steel will satisfy the requirements as well. So that's where you can use rebar. The design mentions in the code that it's all based on smooth bar, but smooth bars or rebar can be used interchangeably here with no negative effect on the design. But you just bear in mind that I suppose you can get further refinement in terms of the anchorage length. Typically, it's double the anchorage length when you're using smooth bars. But you can just follow the Eurocode chapter 8 there on anchorage lengths, and that's really the main base of the calculation of today is the Eurocode anchorage lengths. With lifting loops, we need to consider the effect of the bend radius. So one of the main parameters is, how big is this loop? How tight a radius can you bend? What kind of a chain hook are you putting into it? You can see that the different arrangements here, and there's reasons for different arrangements. You're trying to spread the load. Typically, what you want to do is you want to have the bars, both bars, kind of uniformly working in tension. So this bar here in the middle is best suited to like a pure vertical lift, so no angle in the chains. Both bars will be, the force in them will be evenly distributed. This bar here on the right, it suits an angled lift, where you know what angle the chain is going to be at, and therefore you align the cast-in rebar loop at that angle. Often though, taking all practicalities into account, it's very difficult to know exactly what angle you're going to be at. So you allow for some kind of tolerance. So somewhere in between the two of these can sometimes work, where you have some angle. But in terms of, I suppose, worst case scenario, generally what we do is we just design for the tension capacity of one leg, just to allow for tolerances and the different practicalities on site. I suppose only when you can guarantee that you're lifting vertically and that your loop is vertical, would you have more confidence that the two bars are engaged, so you get the capacity out of the two bars. So next slide. So, sorry, apologies for this pop-ups on my screen here. No. So we can see from the lifting capacity using the rebar, based on the tensile strength of the rebar. So this formula here, basically, we have the tension capacity. N is a function of this K1 factor, which is in this table I'll talk about in a minute, but it's the strength of the bar 2 times the area of steel. So this is saying that you have the 2 bars available to you. And as I said previously, the confidence in that is generally only when you have pure vertical tension lifts. And I'll show what I mean by that in a few minutes. So this K1 factor, it's a function of the bend radius, and it gives some parameters here on allowable bend radiuses with, I suppose, guidance for the hook dimensions as well, and it gives you the factor here. So basically, your whatever bend radius you select, your hook diameter has to be between greater than half the bend radius, basically. So that's here. the diameter of the hook B has to be greater than half of the bend radius, but obviously not bigger than the bend radius itself, otherwise it won't fit. And then depending on which K1 factor to use, you've got your 3 parameters here based on the diameter of the bar being used. So obviously the greater the bending diameter, the less reduction. So obviously the tighter the bend radius, the more of a pinch point you create. and therefore the more concentration of stresses. Other than that, it's a relatively straightforward calculation to carry out, and just bearing in mind again that when you're doing lifting designs, that you need to divide the strength by the partial factor for the material and also the partial factor for lifting and handling. So we'll go through that. Little clause here that states the loading angle should not exceed 30 degrees. So something that you're probably quite familiar with from other lifting designs. So the 30-degree angle. Now that 30 degrees can act in an in-plane and an out-of-plane direction. So we'll talk about that on the next slide. And then the last thing maybe just to talk about on this slide is that this capacity is only valid when you have provided full anchorage according to Chapter 8 of Eurocode 2. Obviously, if you have a small leg cast in to your concrete, the full capacity cannot be achieved before that actual leg pulls out of your concrete. So there's two kind of checks. You check the anchorage length and you check the capacity, the steel capacity. So it's like before, it's a steel check and it's a concrete check. The concrete check is your anchorage bond, and then your steel check is the cross section of your bar. So that's kind of so on the angle, this is a good diagram. Again, this is in the code. All these snippets are from CN 15728, the precast lifting code that I would have spoken about previously. But there are two checks essentially to be carried out in order to determine the demands in the lifting loop. So if lifting is in pure tension, it can be, I suppose, divided evenly like we discussed before. But if lifting is not in pure tension, it means we've got an angle, and these are going to be for in plane and out of plane. So these two beta factors here. So generally you want to avoid out of plane as much as possible. And as I said, you can angle the casting lifting rebar loop to kind of suit the best location for angles. Like if you cast it in vertically like this, but you're actually pulling at 30 degrees, you're going to put a lot more, you're going to get a lot less capacity because of the reductions involved. So for in-plane demands, the distribution of tension force in each leg will be determined, and that's going to be based on the proportions of the height versus the width of the leg. So it's kind of simple statics and a bit of trigonometry. So the it's kind of the reason as well that we want to make sure that regardless of the proportions of the length versus the width here, we still want to make sure that both legs are in tension. Because if both legs weren't in tension, you have compression, one could buckle, a lot more deformation is going to happen of that lifting loop, and therefore it wouldn't be as safe a lift. And that's what you'll find when you do run through the calculations. That's kind of where the 30-degree limit comes from. That for the typical proportions, that if you stayed within 30 degrees, you're going to still have tension in both legs, albeit higher in one than in the other. For out-of-plane bending then, which is this very right-hand image, the effective load will generate bending moments on the rebar. So the bending resistance of the bars need to be checked, and I have some formulas for that as well. Again, they're quite simple formulas, but you don't get as much capacity out of them because you're only bending about a B12 bar, which doesn't, or B10 or B12 bar, maybe B16. But again, that wouldn't have as much bending capacity. So generally to try and avoid bending about out of plane. So therefore, if, for example, you had a slab with 4 loops in it, you kind of want to angle the loops that bit towards the center, so that it does kind of act more in tension as opposed to out of plane. So we're going to look at in-plane demands. And for this, we need to calculate the distribution of tension forces in the two legs. So we can calculate the force in the chains from what we learned back in the first module and all the different factors that went into that module. So, and that's what will become your FV, your vertical force, and all these will have been calculated based on what we have covered in the very first module. and we break it down into the horizontal and vertical components for a given in-plane angle beta. So this beta value here will dictate how much goes into shear and how much goes into tension. The vertical component, so FV, that's going to be split 50-50 into each leg, but it's the horizontal component which acts at a distance B above the surface of the concrete, and that'll generate a moment couple around the two legs. So it'll put more force into one, it'll push down on one and it'll pull out of the other. And simple, I suppose, lever arm formula here, it's your FH times B divided by A, which will give you that. So essentially, we've got to figure out the tension force in each leg, and it's going to be half the vertical force plus the effect of the horizontal force, and in the other one, it's going to be half the vertical force minus the effect of the horizontal force. And what you want to try and do is make sure that this second one here, NED2, is still a positive value, which would be tension. So that's the kind of the aim to check there. And again, your capacity is your design strength multiplied by your area of steel, and the design strength, as I said, needs to incorporate both partial factors when you're lifting. So it'll be FYK over 2.07, and we kind of spoke about that previously. This is all relatively theoretical. I know in practice there's going to be a bit more flexibility in the bar, particularly if you're using smaller bars. They might deform that bit more, but as a general kind of a rule, this would be a guide. And it said, you must make sure they're in tension, otherwise it'll buckle and the loop and lead to failure. So that's kind of that one. And then the last check then is the out of plane demands. So again, simple formula, it's given in the code, but we have all our demands, and the only one we're concerned about here is FH. So FV is just going to be in tension. It's not going to cause any bending moments on the rebar, but when we have a horizontal component in the out of plane direction, it's going to try and bend the rebar, and therefore from the height above the surface of the concrete is our lever arm. You multiply the two of those together and we get our bending moment. Our bending resistance, I've kind of broke it down here. Because it's a lifting loop, it's got two legs, and in this scenario we can avail of the two legs in terms of bending. They're both about the same plane, and it's simple. Moment resistance is time your strength times your section modulus, and your section modulus for a circle is your diameter cubed over 6, and we've got two of them, so therefore it's just diameter cubed over 3. And I've kind of broken down here for simplicity, because when you're using rebar, it's going to be B500 steel, we're going to know what the strength is, so we can put that in here. So it all just breaks down to a function of the diameter. So it's 8.5 times the diameter of the bar cubed, and obviously convert your units then to kilonewton meters. That's your moment resistance, and you compare MRD with MED, and that's your check there to make sure that your bending resistance has not been exceeded. So for both in plane and out of plane demands, you can see that it's best to keep the height of the lifting loop, so this B dimension, keep that as low as practically possible, because as soon as you have any kind of an angle on your chain, it's always going to be a function of the height above the base. So the smaller you can keep that, the better. But at the same time, obviously, you still have to fit your chain hook in under it. So basically, there's a practical consideration as to a minimum of what that can be. That was the steel checks, and I suppose we need to look at the anchorage checks now as well. I mean, there are different ways of looking at this. I tried to create a general formula for it, but I mean, all you need to do is go to Eurocode 2, Chapter 8, on how to calculate the anchorage length. As a rule of thumb, you should always just try to achieve full tension anchorage on your lifting loops. And once you do that, you know then that your weakest component is going to be the actual strength of the bar once you provide full anchorage. This formula here, it is just a culmination of what is in chapter 8 of Eurocode 2. Looks a bit kind of complex, but it's literally just the tension resistance of the concrete. So it's based on anchorage. This formula here, it's a function of the diameter of your bar, the strength of your concrete, the cube strength, and the anchorage length that you've provided. And like I said before, that needs to be less than or equal to the actual strength of the steel. So you can't calculate, you can't, I suppose, stay increasing the anchorage length expecting to get more capacity. You're limited by the actual strength of the steel. So that's all of that kind of states there. So again, it's trying to break it down into parameters that are easily obtainable. So your diameter, your concrete strength, and the amount of anchorage length that you can fit in. There are some, I suppose, good practice rules here that are recommended in the code. For example, that you should be applying a full 180-degree anchorage hook at the ends. It's just good practice rather than leaving it straight. Adding hooks or bobs at the ends, it's always good practice just for that extra bit of assurance. And obviously the structural engineer should consider the shape of the lifting insert compared with the lifting angle. So I spoke about that previously. And in extreme situations, only one leg may be active. So rule of thumb for I suppose, quick designs and stuff like that, if you just assume that only one leg is active, it's also good practice. The next two slides, I think, I'm not going to go through in too much detail. It's just going through how I came up with this formula here, based on the formulas in chapter 8. So I have them referenced here, your concrete strengths. There's quite a number of formulas there, and they all get combined and rearranged. But some of the parameters that are assumed when we're calculating this anchorage, again, it comes down to, I suppose, lack of knowledge in exactly how it's going to be used. So obviously you've got this N1 factor, which 0.7 for bad bond. Generally, your lifting loop is going to be in the top surface, or a portion of the lifting loop is going to be in the top surface of your concrete. So bad bond is a good assumption. Partial strength factors, concrete, lifting, handling, they're still the same. We can avail of alpha 1 equal 0.7 for if we have a hooked bar, which again is good practice as opposed to a straight bar, and the alpha 2 factor of 0.7 when we're away from the edge. And generally, you're always going to satisfy this condition for a lifting loop. You're not going to have, it's not like your side steel in a beam or anything like that, where you're just covering from the edge. And also this clause covers proximity to other bars. So generally, you're not going to have two lifting loops that close together that you're going to be able to not avail of this 0.7 reduction factor. So all that kind of comes in. And on the next slide, yeah, so it just continues on bringing all the formulas together. And we came up with this final formula here of 0.3 pi diameter of your bar, FCK, LBD. So if you know what length you can fit in, because particularly sometimes you have to work backwards just to see what you can actually fit into your beam, etc. If you know what space, you know what depth it is, you can put in your value here and see can you achieve the full strength of the steel or not. And then a quick note on smooth bars, you essentially need to have the capacity when you're using smooth bars. So therefore you need double. If you have the capacity, you need double the length to achieve the same capacity. So depending on whether you're using rib bars or smooth bars, the formula just changes slightly. So this concludes the discussions on lifting using rebar. And again, it's the formulas aren't as complex, and I suppose to put the theoretical spin on it, what we've done in the previous lectures is known as anchor theory, concrete cone, pry out, pull out, all that. Whereas using lifting loops, it's known as a rebar theory, where it's all about anchorage, and that's kind of, I suppose, the theoretical spin on it. Moving on to lifting design using strands. So the approach here is similar to that of rebar. We just have some additional specific requirements to be accounted for. So the diagram here shows typical geometry of lifting loops when we use strands. On the right-hand image, we can see that a steel sleeve is used. So this would be done when we're combining strands to act as one lifting loop. We can do that with strands. We can't do that with rebar. Rebar is that bit stiffer, so that there'll be less flexibility in rebar. But you can combine up to 4 strands according to the code in this manner in the same location. But in order for them to behave as one, there'll be a small reduction factor, which I have in the next slide. But in order for them to behave together, you have to incorporate a steel sleeve that's kind of around the bars, so that the forces get transmitted into them. So on this next slide, yeah, so we've got this K2 factor that gets added to the formula that we saw for the rebar. So K1 FYD 2 times AS, that was the formula we saw before. And now we have to include this K2 factor when we are using rebar strand, and it only applies when you're bundling the strands together. So we can bundle a number of strands to increase the lift and loop capacity, and as I said previously, we have to add the steel sleeve to that. So full engagement of all the strands in the bundle, it can't be guaranteed, and thus we have another reduction factor here of K2 shown here in table 7 of the code. And you can see here for 2 strands, 3 strands, 4 strands, the more strands you have, the more of a reduction factor is there. Obviously, if you've only the 1 strand, K2 is 1. But the more strands that you add together, there's a bit of a reduction factor. And in the final capacity, the lifting loop is the same before, after that. Few other considerations, I suppose little clauses that you can kind of avail of, that when a steel sleeve is used on a single strand, K1 factor may be increased by 25%. So the steel sleeve can be used on 1 strand only, and it just helps with the distribution of the forces and the stresses, and you get a little gain on your K1 factor. The items we spoke about previously, for the angle of beta, so the requirements regarding these loading angles is the same as for smooth bars or rebars that we spoke about a couple of slides ago. So you go through the same process that you did working out your tension and shear. The out of plane, I think there's a clause in there. Again, you want to avoid any out of plane, I suppose, out of plane forces on these, because they are more deformable, and you're going to create a pinch point against the concrete. So particularly when you're using strands or wire loops, you want to try and avoid any out of plane forces on them. And I mean, the anchorage of the strands, it's similar to previous, just with the bond stress, they're different. There's a factor in there. So section 8.4 is your typical anchorage lengths. If you go to section 8.10, that talks about the anchorage for pre-stressing strands and the design strengths, etc. But the formulas remain the same in principle, and it's the same kind of calculation once you know what anchorage you have, and you can work out then what the capacity is. And there's one final type of lift and loop that we're going to discuss today, and that's wire rope lift and loop. So wire rope, smaller diameter to strand in general, and a number of typical examples are given here. Probably the most common type is the one on the right hand side, which is a very typical product provided by lifting device suppliers. It essentially a wire rope loop that has kind of a crimped end to basically make it a loop, and that gets kind of cast into the concrete with a portion of it exposed for your chain hook to engage. The other ones on the left, maybe not so much. I mean, you can kind of unfurl the ends to get kind of a more distributed bond at the end, but the code doesn't allow you to take any. Your anchorage length starts at the solid portion, and obviously it's a bit more messier when you're trying to unfurl, and you know there's a lot of other stuff maybe going on in the cage. So this product here on the right hand side is a nice cleaner product. Again, formula is very similar to before. We have a couple of criteria to be met in order for the wire rope to be used as a lifting loop, such as the minimum number of wires for a given diameter, etc. So that's these here. So depending on what diameter you have, it has to follow specific manufacturing requirements. Even though that the wire rope is much more flexible than the rebar, it's still recommended to adhere to the same rules around the bending radius, etc. that we spoke about at the very start. So that K1 factor, and that's why that's still here in this formula. However, with wire rope, due to its flexibility, we're actually not required to adhere to the same lifting angle requirements that we saw previously. The wire rope will, I suppose, naturally deform to an angle that will allow it to take up the force in pure tension, and that's the kind of the way that this is treated here, so that you don't have to account for the beta angle factors that we saw previously. And again, we can get our two legs from the wire rope, your design strength of the wire rope times your K1 factor, which is for your bend radius and your hook, and then your FYD just needs to adhere then to the two partial factors like we would have had before. Yeah, that just explains the rest of it here. It's just a snippet from the code. Again, look, little practical requirements, particularly if you are using rebar or strand that was kind of, I suppose, left over from other projects. I just need to make sure that's all cleaned. Ends of the lifting loop made of steel wire rope could have a ferrule screwed or split ends. Basically, you want to make sure that the ends are as per what your assumptions are in the design. So if you have a kind of a crimped ferrule at the end, well, then you know that's exactly where you can take your anchorage length from. If you have it split, you need to account for that in the design. So it's only at before the split starts is where your anchorage length can be accounted for. So that kind of covers everything. So I have some worked examples here, if my mouse decides to work. Yeah, so I have some worked examples here that I'm going to go through, and it's kind of the same example 3 times just to give you a sense of the I suppose changes in capacity. So in this example, it's proposed to lift the precast concrete beam at 2 points using B12 rebar as shown below. The rebar loops are essentially cast in vertically with a hooked end. Concrete strength in the factory is C2025 at the time of lifting, and the chains have an angle of 30 degrees, and the rebar is embedded 300 millimeters as far as the hook. So on our diagram here, we've got a value of G equal to 40 kilonewtons. So this value G, it incorporates everything from the first module, the type of lifting equipment, etc. So I don't need to go through all that again. So because it's at 30 degrees, and 30 degrees it's an in-plane demand, it's a beam, there's only 2 lifters. We can work out using trigonometry what the force in the chain is, the vertical force and the horizontal force. And obviously that's all mentioned again in module 1. But we just work through these formulas to basically figure out what the tension force is in each leg of your rebar, based on the proportions shown here, 75 mil above the concrete surface and 100 mil wide. So again, you just got to check all your other your K1 factors and all that. So I haven't shown them here, but basically the capacity here, you can see when you work them out, you end up having 18.6 kilonewtons in one leg and 1.4 kilonewtons in the other, as opposed to an even split of 10 in each. So that angle in plane significantly affects the proportion of load. So therefore, we take the worst case, 18.6, and we check that against our design. So our design resistance, again, assuming all other factors were equal to 1, you'd end up with 27.3. So there should be a K1 factor in here as well, which usually you'd be working to 0.85. So you'd still be within the capacity here. And that capacity of 242 for the strength accounts for the both partial factors for the steel itself and for the lifting and handling. So we have a satisfactory design here in terms of the steel strength. We've shown that both legs are still in tension, and we've shown that the worst case tension is less than the design capacity of the steel section itself. We then got to check the resistance of the concrete, and using this formula from our diagram, we had 300 kilonewtons of anchorage, and the derivation of this formula, like I said, it had the alpha 2 factor equal to 0.7 and the alpha 1 factor equal to 0.7. So they're already included for hooked ends and edge distance, etc. So we can crunch these numbers. So the right hand side of the formula is essentially what we calculate on the previous slide, which was 27.3. And if we only have 300 millimeters of anchorage, we end up with a capacity of 25 kilonewtons. Therefore, you can see it's almost at the full capacity, but we're not quite there. So we take 25 as our capacity in the final state. So in terms of our utilization, worst case demand against the, I suppose, the smallest capacity, and you end up with a utilization of 0.74. And that kind of satisfies that design. So it's 74% utilized. If we change up that worked example then and just went with a straight vertical lift, we can see our diagram here. It gets simpler. It's just a straight vertical lift. We have no horizontal component. So therefore we get 10 kilonewtons evenly into each leg. And those then the capacities remains the same, 27.3 for the steel. And on the next page, we have the same capacity for the anchorage. We still have 300 millimeters of anchorage, and you get 25. So 10 versus 25 is 0.4. So you've almost got double the capacity by just having the by having a vertical lift. So it's one to bear in mind when you're trying to get some of these kind of designs to work. The final example then, often when we try to go for a vertical lift, we always go for a spreader beam. And this is a typical example which you might get caught out on if you opt for a spreader beam to engage all 4 lifters. What I've done here at this example, the previous 2 were a beam with 2 lifters. This one is a slab with 4, and I've just doubled the capacity. Double the demand just to make it comparable. If you're engaging all 4 lifters and your lifting loops are still cast in vertically, well, now if your lifting beam is only a beam, it doesn't have any spreader legs coming off it, well, then you're actually putting an out of plane demand on your lifting loop. So I put in 30 degrees here. That's what the code allows us to go up to. And we just run through the numbers on that. So the in-plane demand doesn't change. So we're going to be governed by the bending capacity of the lifting loop. So because we're at 30 degrees, 20 kilonewtons, we work out similar numbers like we had before, except this time it's out of plane. The proportions of the lifting loop above the surface are still the same, and for out of plane, we're only concerned with the vertical dimension. That gives us our lever arm to calculate our moment, and we end up with 0.116 kilonewton meters of a demand. So we worked out the formula for the bending capacity, so that's given in the code, and it kind of, I suppose, worked it out to be 80.5 times the diameter cubed. So when you pump in that, you get 0.139. Now, I haven't actually done that, so it's 0.116 divided by 0.139. So that gives you you're well above 80% utilized there. Still works, but it's just to, I suppose, to highlight using, for example, a spreader beam. Oh yes, great, we're going to use a spreader beam to spread the load, we'll get a better design. But what are the knock-on effects of using that? Particularly when you're using loops, you're potentially now introducing out-of-plane demands onto your lifter. So just to bear that in mind. So that's the end of the lecture. So we kind of flew through that, but we're kind of bang on time now again. So if anyone has any questions, please feel free to ask.